There is no audio.
Can you on Zoom? Can you hear me now? No, we're not going to do.
Unmuted as well.
All right. Can you hear me now? On Zoom, can you hear me now?
Perfect.
All right. Problem solved. All right. So, all right. So, by the late 70s, early 80s, it was appreciated that these arguments that people used to give for standard model neutrinos would apply to a wide variety of hypothetical particles you might invent for various other theoretical concerns. And these included things like supersymmetric particles, other sorts of exotic phenomena. And by the late 80s, I would say it had become widely appreciated among particle cosmologists that there was this big class of weakly interacting stable massive particles that could have important consequences for cosmology. And in particular, by then, it was appreciated that they might make up some or all of the missing matter or dark matter of our universe. It's not our day. Okay, here we go. All right, so until the last decade or so, WIMPs were the predominant idea for what dark matter can be, and for a really good reason. And I'm just going to, in very broad strokes, sketch what that reason was. So if you make two, I think, really well-motivated assumptions, namely that whatever the dark matter is, those particles were in thermal equilibrium at some point in the early universe. Another way of saying that is that they interact at least a little bit so that they could thermalize and be part of that bath. And then secondly, we're going to assume that the early universe was mostly filled with radiation. That's standard cosmology. It could have been different, but standard cosmology says it's true. If you assume those two things, then these particles that we're talking about, if they're stable, they have to be heavier than a few MeV to avoid ruining the successful light element abundance predictions, BBN, big nucleosynthesis. And they have to be lighter than about 100 TeV. Otherwise, you make too much of it. You make too much dark matter if it's too heavy. So you really had a, let's see, I guess that's 8 orders of magnitude to play with. That's kind of where these particles would have to be. And then furthermore, in that range, if you work out how much these things would have to interact to give you the right abundance, it's weirdly close to this, weak interaction that we measure at particle accelerators. So people started to say, well, this really looks like something in the sort of weak scale mass range, very broadly speaking, with weak scale interactions, broadly speaking, some sort of weakly interacting, weakly massive particle would make up a really good candidate for dark matter. People called it the WIMP miracle. I don't know if it's miraculous, but in my view, it does provide a really nice piece of motivation for WIMPs as candidates for the dark matter of our universe. And then experimental reality kicked in. If you take the abundance of dark matter in our universe and work backwards to what kinds of particles might make up this substance, we end up with a long list of what well-motivated benchmarks and scenarios that you can go and look for in the laboratory. And over the last 10 or 15 years, many of our favorite WIMPs have been ruled out. That's true. Okay. A lot of the stuff that you go read my papers from 15 years ago, the WIMPs I was writing about, most of those aren't allowed anymore. The experiments have ruled out. Over the last 2 decades, direct detection experiments, these are underground dark matter detectors, have performed better than we had any right to expect, in my opinion, exceeding my expectations for sure. And their sensitivity has improved at a rate faster than the famous Moore's law for computing. Okay, so it's exponential growth of this sensitivity to dark matter scattering. And then the Large Hadron Collider in parallel has performed beautifully, but hasn't seen any compelling signs of dark matter or any other physics beyond the state. That's not because it didn't work well. It worked great. It just, the stuff wasn't there to be seen. So let's talk about the impact on our ideas of dark matter of these experiments. So at the Large Hadron Collider, the constraints they've produced are really strong when it comes to particles that can be pair produced in large abundances. So these are particles like squarks or colloquiums and supersymmetric theories, things that are really strongly interacting The LHC has taught us they have to be heavier than a couple of TeV. That's really heavy. Okay, so we used to think quarks and gluinos would be lighter than that. They're not there. Also, things that can be produced on some sort of resonance, like a new vector boson, we call it a Z prime. This is the sort of thing you can look for very effectively at Large Hadron Collider. Haven't seen. In comparison, the LHC isn't really good at looking for WIMPs. It's not blind, but you need kind of a special WIMP for the LHC to see it. So maybe we shouldn't be that surprised that we haven't seen the WIMPs. In particular, you can find a wide variety of supersymmetric models that are consistent with collider constraints as long as these quarks and gluinos are really heavy. That's really the thing you have to do to make supersymmetry okay with the constraints from the Large Hadron Collider. Direct searches, on the other hand, have been a lot more super. Okay. The null results from these experiments have very meaningfully impacted how we think about dark matter, much more than the LHC has, in my view. It's fair to say, I think, that most simple WIMP models generally predict, also generically, I guess, scattering rates of nuclei that are much larger than current constraints. You can build models that lie below these constraints. It can be done. It's not even that hard, but most of the models are now ruled out. That's, I also think, a fair or a reasonable statement to make. All right, so the question that has been asked in light of these pieces of data is, should we consider the WIMP paradigm dead? Should we move on and consider other kinds of dark matter candidates? And I don't think that's reasonable. I think that's an overcorrection to maybe abundance of enthusiasm for WIMPs that we used to have. And the main way, the class of ways that you can evade these constraints is to come up with models that have some sort of mechanism built into them that allow you to deplete the dark matter particles in the early universe. So this is some sort of annihilation diagram or some way of getting rid of the WIMPs in the early universe effectively without having a diagram like this, where you can scatter with nuclei or electrons or whatever in your laboratory. If your model does that, you can probably save it from all of the constraints that currently exist. I'll show you several ways you can do this, but you should just, give me another half an hour. I can add one more thing to the list. It's not that hard to think of more of them, but here are some of the popular ideas that people consider. You might consider models where the dark matter doesn't annihilate with its own antiparticle, or maybe it's itself, but with some other unstable species. So here's an example in a supersymmetric model where the dark matter annihilates with the superpartner of the tau. This is something that can deplete your abundance in the early universe without contributing to scattering in direct detection experiments. You could also have dark matter that annihilates into things that don't exist in large abundances in nuclei. So like here you have something where the dark matter annihilates into W or Z bosons. Nuclei are made of quarks and gluons. You can only scatter with quarks and gluons for this in this model through these nasty loop diagrams, maybe sometimes 2 loop diagrams, and that suppresses your scattering rates to below current constraints. Now, these are things you can test at the next generation of experiments, but not yet. You can write down operators in your model or pick models that have operators where the scattering is suppressed at low velocities or low momentum transfer by various powers of these things. And since the halo consists of, the nucleus halo consists of dark matter particles that are moving very slowly, this gives you huge suppression factors, explaining why you wouldn't have seen those candidates in our experiments yet. A fourth way is you can just imagine the dark matter is pretty light. The direct detection experiments we have that are really powerful only at a few GeV and above. So we can build models down here, and those work perfectly well. You could have dark matter as low in mass as a few MeV without really having any cosmological problems. That all works pretty well. It's not very hard to do, and this whole parameter space is more or less unexplored, at least up to this point. Instead of playing with the particles that make up the dark matter, you might play with the context that they were created in, namely the early universe. So we don't have any direct way of inferring what forms of matter or energy dominated the energy density of the very early universe in the first second or so. I gave a talk yesterday about scenarios where black holes were very abundant during this era. That's just one possibility. And in light of that, you could write down a wide range of speculative but reasonably well motivated scenarios where the early universe might have had a matter dominated or other exotic era. And when you start putting things like that, you get very different expectations for what kind of dark matter would be produced and what abundances. And you can definitely find ways where the dark matter could be produced in the right abundance with an exotic early universe cosmology without coming into conflict with any of the existing experiments. And then the sixth and final thing on my list here is that you could imagine dark matter that is part of what we call a hidden sector. Now, I imagine a lot of you haven't encountered hidden sectors before, so I'm going to spend a few slides kind of explaining what I mean. And also just because I think it's a cool idea. It's kind of a nice playground for a particle phenomenologist like myself. The idea is this. So we know of a bunch of particles in the universe: electrons, quarks, neutrinos, photons, muons, etc. WZ6. All of those particles, we are able to infer their existence because they interact through one of the three forces of the Standard Model, one or more: strong, weak, or electromagnetic force. Some of those particles interact through one or two of the forces, but not the others, and et cetera. So it's super plausible to imagine that there might exist other particles that don't interact through any of those forces. It's kind of a selection effect. The ones we know about are the ones that interact through the forces we observe. So there will be some others that don't interact through those forces, and we don't observe them because of their lack of interactions. There might even be forces that those particles interact among themselves with that we aren't privy to. So maybe there are things like, so whereas electromagnetism is in the Standard Model is communicated by the exchange of photons, maybe there's a hidden sector photon that exchanges or communicates a different force, a hidden sector electromagnetism between those particles. That's all very, very plausible, very, very easy to write down theories to do that. So here we have the Standard Model and all of its particle content. All those particles can interact among themselves. There's three known forces. And then there's some other set of particles. I'm being pretty vague about what I mean, but some other sort of particles, they have their own forces and other characteristics. And then there are only very weak portal couplings that allow the two sectors to interact. So in terms of dark matter, you might have a situation like this. We have my hidden sector particles X. They do not directly couple to the Standard Model in any way, but they annihilate into other hidden sector particles, Y. The Y particles can interact with the Standard Model through this very, very feeble portal coupling, causing them to eventually decay. This could even be a long lifetime. This could be a really slow process, but who knows, giving a Standard Model. So if this is the sort of particle physics setup you cook up, then this process is what sets the abundance in the early universe. And then is this decay, which has nothing to do with the abundance, that allows that energy to go from the hidden sector into populating the normal thermal back that we recognize in our universe. This solves a ton of problems that a particle cosmologist might want to solve. For one thing, you can easily get the right Welk abundance. You basically need weak scale particles with weak scale interactions, all in the hidden sector. Works just like ordinary WIMPs. Direct detection, though, is really suppressed because it relies on these portal couplings, which can be almost arbitrarily small. Production of colliders is highly suppressed for the same reason. And the model building is really simple. You can just write down stuff that right out of the box you know will work. These renormalizable operators, they call them the vector Higgs and lepton portals. I don't have time to explain them, but like they're kind of the simplest thing you can write down, and they just work to connect the hidden sector you might postulate with the Standard Model. It works beautifully. It's very easy to do. All right, so here are 6 of my favorite ways you can try to make a WIMP be viable in the current experimental situation. And I think this list, among other ideas, give you a really good list of reasons why you shouldn't be dismissive of WIMPs. WIMPs could very well make up the dark matter of our universe. I even think it's likely, if I'm being honest. But the title of my talk is not, reasons why you shouldn't give up on WIMPs. It was reasons why you should be excited about WIMPs. So now I'm going to pivot and not just tell you why this isn't ridiculous to keep WIMPs in mind, but instead why we should maybe be more optimistic about them than we would have been 10 or 15 years ago. A recent development has to do with this property called the Muon's anomalous magnetic moment. So if you just take the standard model, you can calculate the magnetic moment of the muon at tree level, meaning basically the classical calculation. You get a value of 2 for this quantity. We define this in A of mu, which is G minus 2. So that's why they call this thing G minus 2. And then if you calculate the loop corrections at one loop level, it's a little bit different from the classical result at 0.2% or 0.1% or something. And then you can calculate these things up to about 3 loops in modern calculations. You can determine the magnetic moment to a few parts in 10 to the 7. So really, really high precision. And these are the sorts of loop diagrams theorists have spent their whole careers doing. It's really an incredible project. In the early 2000s, I remember when it was announced, I was a grad student in Brookhaven National Lab, had an experiment to measure this quantity. And they found that their measured value of the magnetic moment was different from the standard model prediction at a level of about 3.7 standard deviations. We were all very excited. We all thought we discovered Susie. That's probably a little bit overly enthusiastic for the time, but like that's what people were talking about over beers at the University of Wisconsin Student Union that week. And then a lot of time passed and not a lot changed in the story. But just this year in April, the Fermilab G-2 collaboration confirmed this result, the Brookhaven result. Alone, Fermilab's result conflicts with the standard model at 3.3 sigma. And when you combine it with Brookhaven, you get about 4.24 sigma, evidence for departure from the standard model. So here are the measurements, and here is the standard model prediction. And these two things are 4.2 sigma discrepant. So I would argue, and I think this is fair, that whatever the explanation is, it's probably not just some mistake or some statistical fluke. 2 different experiments operate in 2 different parts of the country at 2 different times by largely different people and different apparatus, found the same result. Okay, that would be quite a coincidence if they just made the same error in 2 totally different apparatus. And 4.2 sigma things don't happen by accident very often. Okay, this is more than statistical likelihood would allow you to contemplate. What I'm more worried about, like if this isn't new physics, it's probably that the theorists calculated things wrong. I'm more worried about that. After all, this is a very hard calculation. The significance of the G-2 collaboration generally quotes is based on these R ratio determinations of the standard model prediction. These are empirically driven techniques. So you go to a collider, you measure some specific quantities which go into part of your theory calculation. So it's not a purely theoretical calculation, it's a theory plus empirical method. And when you do that, you get these theoretical predictions here, which are very different from the measurement. But on the other hand, there are these other theoretical calculations based on lattice QCD, so simulating the effects of quantum chromodynamics on a computer lattice. And those have much bigger error bars, but they're maybe closer to the measured value. So I think it's going to be really important for us to improve these measurements, squeeze those error bars, and find out when they get smaller, do they kind of prefer this sort of value or this sort of value? Because that makes a world of difference. I think this is something that will happen in the years ahead. But right now, this is the thing that makes me not completely sure this is new physics. Okay, so before the LHC era, when people talked about G-2, they usually talked about it in the context of supersymmetry. So in particular, they had diagrams like this in mind that would contribute to the anomalous magnetic moment of the muon. So here's a loop involving muons and neutralinos. Here's a loop involving charginos and a neutrino. these sorts of diagrams can give you the sort of contributions you want, so long as the masses of these particles in these loops are, in the ballpark of a few hundred GeV, and this parameter called tan beta is pretty large. It's like kind of right out of the box supersymmetry. That looks pretty good. Some of the SUSY models that do this have been ruled out by the LEC, and others haven't. So I think this is still a very reasonable possibility. And as far as dark matter is concerned, this particle could be our dark matter candidate. That's pretty interesting. And furthermore, like this kind of class of models that could explain the G-2 anomaly could give you a really good dark matter candidate, especially in these corridors of SUSY parameter space called the SUSY blind spots, where the direct detection experiments are not very sensitive. This is a pretty good way to think about the interpretations of this anomaly, and it does point you in the direction of very attractive WIMPs in the form of supersymmetric dark matter candidates. All right, so next, I'm really going to spend the bulk of the rest of the talk talking about this signal, the Galactic center gamma ray excess, which Louis mentioned in the introduction. So this goes back to 2009 when Lisa Goodenuff and I first saw this signal in the publicly available Fermi data. At the time, I thought this is kind of interesting. It looks like the WIMP signal that we always had in mind. As time went on, I would say by 2014 or so, I started to be pretty convinced this was WIMPs. I wouldn't say that I'm certainly not certain that it's WIMPs today, but I think there's a pretty good chance that WIMPs are annihilating the Galactic center, making the signal. That's probably, if I'm being honest, the main reason why I remain so enthusiastic about WIMPs as dark matter candidates. So I'll try to give you an idea of the characteristics of this signal, the arguments that have been made in favor of a dark matter interpretation, the arguments that have been made in favor of other interpretations, and where things stand now, and what we can do to test the various hypotheses. Okay. So the overall shape of the signal on the sky, what we call the morphology of the signal, it looks to be approximately spherically symmetric with respect to the galactic center, just like you'd expect a dark matter signal to look like. Quantitatively, the axis ratio of the thing is within 20% or so of unity. And the flux falls off like the distance to the galactic center to about 2.4 power, at least out to 10 degrees, where it starts to be hard to see. If you interpret this as a signal of annihilating dark matter, it tells you that the dark matter halo profile in the inner part of the Milky Way goes like the distance to the galactic center to the minus 1.2 power, which is just a little steeper than 1 over r, which is what you get from the canonical NFW profile of forever. In other words, this is basically what you expect from dark matter annihilation. Unlike stellar populations, we expect the dark matter annihilation products to be approximately spherically symmetric. The bar and bulge and disk of the Milky Way are all extended along the galactic longitude axis. And that is not what we see in the signal. The signal looks to be approximately round. So it's hard to explain the morphology of the signal with traditional stellar populations. Next, the spectrum or energy distribution of the photons we're detecting here is consistent with a roughly 20 to 65 GeV particle annihilating to quarks or quarks or gluons. Depending on the types of quarks or gluons. So for example, if you're going to bottom quarks, you want a mass in the range of 40, 45, all the way up to maybe 55 GeV, something like that. And you can see from different channels, you get different answers. And furthermore, it's an important test that was done by these authors that you get the same shape of the spectrum when you look in different parts of the gamma ray sky. So here, for example, if I look in region 1, I get this spectral shape. And if I look in, region 10, the corners here, I get the spectral shape. And it's consistent with the same shape up to statistical uncertainty throughout the whole region. This is important because it tells you it's not something like cosmic electrons that can cool as they propagate out through space, having different spectrum, different parts of the sky. This is something that's uniform across the entire inner galaxy, other than the fact that it gets fainter as you go farther out, as you expect. So this allows you to discriminate between various hypotheses in an important way. The third feature is the overall intensity of this axis. So if you want to normalize the observed signal with dark matter annihilating in the inner galaxy, you need to give those particles a cross-section, annihilation cross-section that's within a factor of 2 or 3 of 10 to the minus 26 cubic centimeters per second, which, by the way, is almost exactly the number you need to explain the relative abundance as it was produced in the early universe. So let me kind of put this in context. If I picked up a textbook discussing production of dark matter in the early universe, I picked up a copy of Coleman Turner's The Early Universe from 1989. I flipped to the chapter called The Origin of the Species, which is about WIMP freeze out. And I took from that, well, how heavy, what annihilation cross-section, and how should these things be distributed in the Milky Way? I would find, basically, they told me all the same things that we see in the Fermi data. So that could be a coincidence. It could be. But in my opinion, when I look at this, it looks like exactly the thing that we've been looking for 30 years. And that has left me very excited about the prospects that this might have something to do with dark matter. A wide variety of other interpretations have been discussed in the literature. Most of those haven't panned out. As the data have gotten better and the calculations have gotten better, most of those things have been ruled out. At this point, the discussion is almost centered along the lines of these two hypotheses. So a lot of people still talk about the signal being the product of annihilating dark matter, but just as many, if not more, papers are being written these days about the possibility that there could be a large population of millisecond pulsars in the center of our galaxy that are producing this gamma ray emission that kind of mimics a dark matter-like signal. So a little primer on what millisecond pulsars are. So pulsars more generally, not just millisecond, but all of them are rapidly spinning neutron stars who are gradually converting their rotational kinetic energy into various kinds of radiation. This might be beamed radio emission or beamed gamma ray emission or even X-rays and things like this. Typical pulsars, what we call young pulsars, exhibit periods typically in the order of a second or so. And they slow down and become faint, losing the rotational kinetic energy over a time scale of 1 million or a few million, or something like that. In terms of the period of a pulsar and the time derivative of its period, these are the pulsars I'm talking about. These are the young pulsars. And as they evolve, as they spin down, they move along these lines of approximately constant magnetic field, getting fainter and eventually falling into this region we call the pulsar graveyard. One of those graveyard pulsars, that can sit there for a long time, billions of years, could either have or acquire a stellar companion that can then transfer into the momentum to it, spinning it up and kind of revitalizing the pulsar, giving it a second life. These pulsars have lower magnetic fields. They're down here. They have much faster periods, typically in the ballpark of a few milliseconds to a few tenths of milliseconds. And because their magnetic fields are so much lower, they evolve much more slowly. So their periods are just spinning much more quickly, but they slow down much more slowly. So they can stay bright, not for millions of years, but for billions of years. And if you do the calculation, you just ask how many of these there could be in the inner galaxy, the answer is you don't get very many because they get faint too quick and they disappear. But over the course of the Milky Way's history, a large number of these could have built up, giving us a kind of integrated gamma ray signal from all of those millisecond pulsars that accumulated over many billions of years. This is kind of the executive summary of arguments that are commonly made either for or against the interpretation of the galactic center gamma ray access in terms of millisecond pulsars. The obvious and most powerful argument in favor of them is this first one. Namely, the spectral shape that's observed from millisecond pulsars elsewhere looks qualitatively similar to the galactic center gamma ray access spectrum. The shape of the spectrum looks similar. That makes you think that this might have a common origin. That's a good argument, in my opinion. And this is not up there as a joke. People laugh at it sometimes, but that's a really good reason to weigh pulsars more highly than dark matter. We don't know that WIMPs exist. We do know that pulsars exist. So put that into your Bayesian calculator. The third point is that there, over the last several years, have been a number of papers have claimed that there's small scale power in the gamma ray emission from the inner galaxy, namely that this emission looks clumpy, which suggests it's not coming from dark matter, but it's coming from point sources like pulsars. This turns out to not be a good argument. It is now, I would say, effectively falsified in light of more sophisticated analyses that have been done. I'll explain that a little bit later. And then another argument has to do with the detailed morphology. Some groups have argued that this isn't really spherically symmetric, but instead the excess traces things like the distribution of the bar or bulge, things like this. I'm going to argue again that this is not a good argument. So these 2 points, I think, are good points. You should keep them in mind that they're good reasons to weigh the pulsar hypothesis reasonably highly. These two, I don't carry any water at all. I would encourage you to ignore those. On the list of arguments against pulsars, and then kind of by default in favor of dark matter for this signal, we should keep in mind we've never seen a millisecond pulsar anywhere near the inner galaxy. That's surprising. If there were so many, if there were really tens of thousands of these things in the inner galaxy, you would have expected to have resolved some by now. So that's kind of an issue, and I guess that's connected to this luminosity function point. And then secondly, if there were enough millisecond pulsars in the inner galaxy to generate the signal, you should have expected to see far more low mass extrabinaries in this part of the sky as well, and we haven't. So I would say that this doesn't prove that the signal couldn't come from pulsars, but it proves that if the signal comes from pulsars, these pulsars are qualitatively different in population, at least, than the pulsars we see in other parts of the Milky Way, whether it be globular clusters or in the field of the Milky Way. So it's possible, but there would have to be a kind of a different population there that we have never seen before. Okay, so let me go through a little bit of the story about these groups that claim the evidence of point-like emission or a point source population that's responsible for the galactic center excess. It started back in 2015 with these 2 different papers. I think they came out the same week, if memory serves. And what they both found using very different techniques was that the GeV emission from this part of the sky wasn't smoothly distributed in space, but instead came in little clumps of photons. There were more pixels, if you were, with several photons in them than they would have expected if dark matter were producing a signal. The Lee et al. Group used a technique called the non-Bosonian template fitting technique. It's a really clever technique. I think very highly of it. But it turns out that it runs into some problems, but the technique itself is a very interesting one. And when they carried out their execution, they found that the signals appeared to them to be clumpy, indicative of an unresolved point source population. And then this Bartels et al. Group reached a qualitatively similar conclusion using a very different technique using mathematical objects called wavelets. So let me kind of describe what a general template analysis of Fermi data looks like, and then what the Lee et al. Group did to supplement it in their non-Bosonian technique. So what you normally do is you sum a bunch of different maps, okay, different spatial templates on the sky in a given energy band. And you have the coefficients of those different maps float arbitrarily until you find out what the best fit normalizations of each of them are, and this allows you to extract the spectra of each of the templates. What Lee et al. Did is add to them a group of non-Bosonian templates. So all of these, if a given pixel said there were, you expected there to be 30 photons on average in this pixel, you'd have a Bosonian distribution around an expectation of 30 that you would draw from, and that would be used to determine the likelihood. These non-Bosonian templates are different. Depending on the luminosity function you observe, it might be that if your average is 30, most of them will be 0, and occasionally you'll get one that's 200. Okay, so this would be an example of a clumpy distribution of gamma ray emitters. Okay, so a smaller number of sources than you have pixels would show up in these templates as opposed to these. And here's one of the results from that paper. So this is basically a measurement of the luminosity function of the different point sources they were inferring statistically. So these are the brighter sources, they're fainter. You can see that they actually get correctly the bright sources that are part of the disk population. But they also found evidence here for this kind of bump-like feature in the luminosity function. So in other words, at about 10 to the minus 10 in these flux units, they were finding there were a lot of sources, a lot more than you would have extrapolated from the disk alone. And just for context, this is approximately where the threshold for the detection by the Fermi telescope comes in. So this is where Fermi can clearly see things. Here's where Fermi can like just barely begin to see things. And here you can't see anything with Fermi at all. So the idea here is that you could explain the galactic center excess without dark matter if there's a bright or a large number of point sources that are right around Fermi's detection threshold in brightness. So the problem with this sort of technique is not that it doesn't work mathematically. On paper, it works. But if you have imperfect templates that don't really capture all the detailed structure of reality, you can end up fooling yourself into reaching false conclusions. So for example, let's say this is some direction in the sky and here's the flux you observe. Let's say you observe this black line here. One way you could interpret that is saying, here's what all the backgrounds look like, the diffuse emission from pions and Hertzsprung and inverse Compton scattering and whatever. And when I do a subtraction, I learn this is what my excess, the galactic center excess signal looks like. And look at all that structure. Look how clumpy that looks. That looks like point sources. Conclusion, right? But maybe you should interpret it like this instead. Maybe this, you observed exactly the same thing. The black lines are the same here. And this is the smooth dark matter-like signal. When I take the difference, I get this. So in fact, this smooth template, this overly simplified background template I've been using wasn't adequate. The real one looks more like this. So these little clumpy features aren't coming from the galactic center excess at all in this frame. Instead, they're coming from the detailed emission associated with those poorly modeled templates. And I'm going to argue, I will argue, that the current data and our current understanding of the galactic diffuse emission mechanisms don't allow you to tell which of these two things is going on. A paper that I think clarified the situation considerably came out in 2019 by Rebecca Lean and Tracy Slatcher. I think very highly of this paper, so let me kind of walk you through the bottom punchline of it. So they make plots of this sort of nature. So this is actually an old plot from the 2015 Lee et al. Paper, which Slatcher was an author of, by the way, so it's the same Slatcher. And what they do is they float all these templates, Poissonian and non-Poissonian, and they find out how much total emission is attributed to each. So for example, in this case, this is the bit from dark matter, and it's consistent with 0. There's really no evidence of any flux from a smooth dark matter-like signal. And then this one, this is the piece attributed to dark matter squared distributed point sources. So the excess, according to them, wants to overwhelmingly come from point sources like pulsars and not come from something smooth at all. And what Lean and Slatcher were trying to address in this 2019 paper is, to what extent could these problems with these templates bias these results, change the results away from truth? So here's the same result that Lean and Slatcher get using exactly the same procedure that Lee et al. Used in 2015. So then after they did that and reproduced the Lee results, to test the reliability, they took the real data, the real Fermi data, and added a simulated signal of dark matter. So because they added it by hand, they knew the signal was smooth. The question is, will the analysis pipeline identify it correctly as a dark matter-like signal, or would it misattribute it to something else? And here's what they find. The dark matter bit is 0, and it's still 0. It hasn't moved at all. But this point source bit, which was just a little over 2% here, it's moved up to like almost 4%. It's gone up. So you put in dark matter signal by hand, and the pipeline tells you it's more point sources. That doesn't look good. So let's even crank it up further. I guess I just said that in words. What happens if we add an even larger dark matter signal to the data? It just keeps giving it the pulsars, to point sources. you can make this like many times brighter than the real galactic center excess, and the pipeline wants to call it point sources. So what's really going on here is that those templates are artificially smooth. They don't contain all of the real small scale power information that exists in nature. So the templates are looking for somewhere to put that small scale power, and they put it in the galactic center shaped template. And this just shows that this method won't work given the templates we have available to us right now. The bottom line is that the non-Poissonian template technique is clearly misattributing the dark matter light signal to point sources, demonstrating the templates being used in this analysis are just simply not adequate to describe the data, and then this strongly biases the results of the fit. The method certainly does not provide any evidence for point sources, but I would say it also doesn't provide any evidence for dark matter. It just shows that this technique can't tell the two apart. I won't get into it in detail, but the wavelet story is actually very similar for very similar reasons. The wavelets, again, rely on how we model some of the backgrounds, and we don't have the good models for those at small angular scales, and therefore we can't tell if the excess signal is in fact smooth or clumpy. So the second thing in my list of reasons to argue in favor and against pulsars, the other thing I mentioned that I said wasn't a good argument were these morphological arguments about whether the excess looks more spherical like a dark matter halo or more shaped like a bulge or bar or something like this. And this really comes from these three papers by the Macias et al. Group and the Bartels et al. Group. And it turns out that just the answer you get, even these three papers reach different answers, even though they all argue against the dark matter interpretation. And just the details of exactly how you carry out this analysis, exactly which templates you use, exactly what your region of interest is, how your energy binning works, how you treat point sources, how you treat the Fermi bubbles. All these things lead you to get qualitatively different answers. And just to give you another example, just earlier this year, the Demaro wrote a paper. It might have been Demaro et al., I'm not sure which. And he reached an entirely opposite conclusion. He said the data strongly prefer a spherical symmetric template. So I just don't think we know at this point. There's nothing in the data that we can robustly say better fits a dark matter template or a bulge or any other kind of template at this point. All we can say is that qualitatively, there's a roughly spherical signal that falls off roughly like r to the minus 2.4. Whether or not it has the detailed structure of the bulge and bar system along with the central molecular zone, or whether it looks more like a dark matter-like signal, I think we just can't tell until our templates qualitatively improve. And one thing I just want to emphasize, because those Macias et al. Papers were arguing to the contrary, is that no millisecond pulsar has been detected in the inner galaxy. For that matter, no real candidates for millisecond pulsars have been detected in the inner galaxy. This paper argued that these 3 millisecond pulsars are likely part of an inner galaxy population. But all you need to do is look it up in the catalog. We have parallax measurements to all of them, and none of them are located in your inner galaxy. So they're just wrong. Okay, so let's ask, in the last few questions or minutes, let's ask the following question. So if this is real, if there really is annihilating dark matter particles in the inner galaxy creating the gamma ray signal, where else would we expect to see evidence of this process? And I think one of the most direct corollaries to this would be you should expect to see it in the cosmic ray spectrum. So an excess of cosmic ray antiprotons was pointed out in 2016 by 2 different groups, this Cuoco et al. Group and the Kai et al. Group. Both groups identified a small but pretty statistically significant excess. I think they were claiming between 4 and 5 sigma in either paper. And what I would say these papers successfully argued is that if you took right out of the box cosmic ray models based on programs like Galprop, and you didn't do anything fancy, the fits improved dramatically when you included an annihilating dark matter particle in the halo of the Milky Way, with a mass of about 40 to 70 GeV and a roughly thermal annihilation cross-section, which, if you recall, these are the same numbers approximately you need to explain a gamma ray signal. So I looked at this with a lot of enthusiasm at the time, but let's also acknowledge this is a really small excess, right? It's just kind of a small weak bump over backgrounds. It looks like a rich area for something to go along. It wouldn't take something very dramatic to fake a signal like this because it's so small. All right, so these 2016 papers didn't get that much attention, 100 and something citations each. Not bad, but for a papers claiming 4.5 sigma evidence for dark matter, you'd maybe expect more attention. It turns out the community was pretty skeptical of these results. And the skepticism was based on concerns about the systematic uncertainties. In particular, they were worried about whether they were really modeling the cosmic ray injection and transport in the interstellar medium adequately. They worried about the production cross-section of antiprotons, something you can in principle measure in a laboratory, but haven't been measured that well. And also the impact of solar modulation, or basically solar heliospheric effects as cosmic rays come into the solar system. I would argue that the 2016 papers and subsequent papers have now thoroughly explored this first point. That's probably not the answer. That probably won't explain why this bump appears there. That doesn't seem to be part of the story. And I would also argue that solar wind now has been much better understood. Works by Elias Cholas and others have really improved that situation considerably. And the antiproton production cross-section is improving as we speak. We're not quite there yet, but I think at this point it's clear to say that if you want to explain this excess with cross-section uncertainties, you need to kind of put in a weird bump feature in that. And maybe you could do that. Stranger things have come up in QCD, but I would say at this point there's no evidence for that. Okay, so after marginalizing over the uncertainties best we could, we found a picture that looks kind of like this. So this is for a particular channel, but you could do it for other channels. You get qualitatively similar answers. In this region, things are ruled out because we should have seen a gamma ray signal from dwarf galaxies, but haven't. In this region is where you can explain the galactic center excess just fine. And in this region, you could explain AMS's antiproton cosmic ray excess. So for something like a 50 to 70 GeV WIMP, something in this range, and a cross-section in the ballpark of 2 × 10⁻26 cubic centimeters per second, you explain both of these signals in a pretty self-consistent way without conflicting with any existing constraints or null results. Looking forward, I think a really important thing will be radio searches for millisecond pulsars in the inner galaxy. If you could wait to something like SKA to begin to take substantial amounts of data, you should expect to detect hundreds of these millisecond pulsars in the inner kiloparsec or so. Either those are going to be there or they're not. If SKA gets their 100 hours of in the inner galaxy and only sees a small number of millisecond pulsars, I think we can just rule out that interpretation. In the more interim time scale, you might even be able to see some of these with the Green Bank telescope, and Meerkat looks really exciting. Meerkat's already been detecting new millisecond pulsars, but not near the galactic center yet. With an adequate amount of time in the direction of the galactic center, Meerkat could be quite informative. So I'm pretty excited for Meerkat surveys and also in the longer run for something like SKA. All right, so I'll just spend a minute or so summarizing. So direct detection experiments have done spectacularly well over the last couple of decades, improving exponentially with sensitivity. And these results have put considerable stress on the historic WIMP paradigm. There are, however, lots of WIMP scenarios that can evade these constraints. I've talked about several ways to do that. It's not particularly hard, but it does require some awareness of the different model building options. The parameter space below the current direct detection constraints and above the neutrino floor includes a lot of very interesting models. So in that order of magnitude and a half or something that still looks experimentally probable but not yet probed, I have a lot of hope that a signal could be found there. So I'm really excited to watch these xenon-based detectors advance, and at lower energies, a variety of other technology, or lower masses, a variety of other technologies explore the range between current constraints and where the neutrino backgrounds begin to kick in. The Fermilab confirmation of the G-2 anomaly, if correct, points towards new physics at or around the weak scale, or at or below the weak scale, I should say. And this you could very easily involve physics of something like a web, something like a dark matter candidate or a sector of particles that include a web. And this includes SUSY, but other web-friendly frameworks as well. And then I spent a fair amount of time in the talk talking about the Galactic Center excess, which remains close to my heart. I think it's very compelling as a prospective dark matter signal. It's certainly not the only interpretation that can be offered at this time. But I think it is fair to say that it's difficult to explain with known or proposed astrophysics. And there are a lot of ways forward to clarify the situation, whether that is using the cosmic ray spectrum or studies, gamma ray studies of dwarf galaxies, or deep radio pulsar searches in the inner galaxy. So I'm excited about all these things. I'm also just excited to be here talking with you all today about science in person. I haven't had an opportunity to do this in a long time. Thanks for the opportunity. Thanks for the invitation. Especially thank you, Louis, for being such a great host. And just one slide of shameless self-promotion. It's my most recent book, At the Edge of Time. People seem to like it. If you're looking for a popular exploration of the early universe, this could be up your thing. And if you're more of an audio person, Why This Universe? I'm a co-host with Shalma Wegsman, who's a grad student at NYU. We're slowly building in popularity, little 30-minute explainers on stuff we think is cool in physics and things adjacent to physics. So thanks again for having me. I'd be happy to talk to anyone or take questions and talk to anybody afterwards if they have any questions that they'd like to prefer to discuss in that context.
Thanks, Jan. Let's give that he's actually taking topics, suggested topics for a podcast. I was actually put on the spot. I felt really nervous at any suggestions, but if anybody has any suggestions for things you can talk about, I'd love to.
The first year was easy to think of ideas, and the second year is a little harder.
Okay. Okay, so let's open the floor up for questions. Grisha, if you want to just state the question, and then you can repeat it for the audience.
Oh, okay, yeah. So yeah, first of all, thank you very much. It was exciting talk. So the cross section that you're referring to seems to be rather high, in fact, right? So it's probably on the order of 10 to the -36 centimeters squared, right?
Yeah,
if you just take the speed of light, right? The annihilation. The detailed balance principle would indicate that the inverse should be of the same order of this, the inverse cross section, right? So then one would think that it should have been observed or produced at LHC. And then the question is, why haven't we seen? Because the cross section you're referring to is not small compared to the integrated luminosity of LHC, which is now by now hundreds of inverse femtobars, right?
Okay, so I'm going to paraphrase the question for our listeners on Zoom. He correctly pointed out that the annihilation cross section I'm talking about, and this is a signal B, but whatever, it's like in the ballpark of 10 to the -36 square centimeters. So let's put that in, and that's about a picobar. Okay, and he then argued that a picobarn is